then I was thinking, like, is there a neat way, like, is there something I can point to and say, look, this is where it deviates from intuition? And I thought, well, it's because it's a spinning thing. You know, the physics of spinning things is counterintuitive because you've got the moment of inertia with this r squared term. Like, maybe that's why. Maybe it's just because the physics of spinning things is weird and we don't have an intuition for it. But then I was talking to Henry from Minute Physics about it, and now I think I'm wrong.
Hey Steve, so when you first told me about this lever paradox puzzle thing, I also thought it must be because rotating things are complicated, but when I sat down and did the calculations, I noticed that I didn't really have to rely on any physics specific to rotations. Ultimately, the two different masses are distinguishable when you waggle the lever purely because they move different distances. The little mass on the twice as long lever moves twice as far for a given deflection of your hand. This got me thinking about other places where an identical force applied over a fixed distance can result in objects moving different distances, which made me think of pulleys. Like, you could hold up a 1 kilogram object with a rope over a pulley like this, or a 0.5 kilogram object with a pulley set up like this, and the force you'd experience would be the same. Feel free to pause and think about it. For you to pull your rope 1 meter, the 0.5 kilogram object will move 2 meters, while the 1 kilogram object only moves 1, just like the rocket lever thought experiment. And the rest of the math works out identically to the levers. If you hid these two pulley setups inside boxes, you could tell which was which by pulling up and down on the rope, the equivalent of wiggling the lever. It's kind of like the pulley setup gives the small mass a higher moment of inertia, or whatever the equivalent of that is for pulleys. And you can also contrive a similar but not exactly the same situation with inclined planes. So I think this whole puzzle is more about the mechanical advantage of these scenarios. At least mechanical advantage applied in such a way that it results in an object moving a different distance than your input force moved. Because, full disclosure, there are also ways of setting up a situation with inclined planes where you really can't tell the difference between the two different masses because the force you experience is the same, and they both move the same amount. So I think it's about how mechanical advantage allows you to convert the magnitude of the motion.
So really it's about mechanical advantage, which interestingly was the central premise of my last video about Brennan torpedoes. Total coincidence there. The famous thing about mechanical advantage is there's a trade-off between force and distance moved. I don't require much force to move this mass up and down because I have mechanical advantage, right? But to get the mass just to move a little bit, I have to move my hand a lot. And I guess we can just extend that. So it's not just a trade-off between force and distance. It's a trade-off between force and distance over time. In other words, velocity. It's also a trade-off between force and distance over time squared. In other words, the acceleration. So to apply that back to the waggly sticks, look, in this scenario, we actually have mechanical disadvantage. So let's look at what happens if we give ourselves mechanical advantage, right? So we're going to double the mass, but bring it closer to the pivot. And now it's easier to waggle, but we have to waggle it further. And it's going to waggle faster. And it's going to accelerate more rapidly too. On the other side, if we've got mechanical disadvantage, then the force is larger, as we could feel, but also the distance traveled is smaller, and the velocity is smaller, and the acceleration is smaller as well.
Hey, this is Henry butting in here again. I want to add one other reason I suspect your original puzzle feels counterintuitive. I think we're used to thinking about the experience of applying a force for a given amount of time, like holding a 1 kilogram weight for 5 seconds. But if you tell me I'm going to apply a force over a given distance, which was the original setup, while that sounds super similar to our brains, it's actually a very ambiguous statement. Lifting a 1 kilogram weight a meter could take 5 seconds or 5 hours, and those would be very different experiences.
Yeah, that makes sense. I like that. Any other theories from viewers, you can let us know in the comments. But what does all this mean for my double-decker Newton's cradle? Well, when you're trying to figure out where the ball needs to strike the lever, you're trying to figure out the position that would cause all of the kinetic energy of the ball to be transferred to the lever, just like you would if it was a ball colliding into another ball. Like if it was just the ball and the lever, you'd want the ball to stop dead and the lever to start spinning. And when you do the maths, it turns out you have to match the moment of inertia of the lever and the ball about the pivot point.